We now discuss generation of angle modulated signals, and we have two parts: the narrowband angle modulated signal and the wideband angle modulated signal. And for us to start us off, we require the equation 416 that we defined as one unmodulated carrier with or added to another modulated carrier that is a function of phi of t, whose the signal of the sinusoidal component has been phase shifted by 90 degrees as defined in equation 416. And we also define equation 417 that define the narrowband phase modulated signal, and equation 418 that defines the narrowband frequency modulated signal. Therefore, for us to generate that, we can directly look at this equation and see how we can generate each of these signals. This is purely you have a local carrier that is unmodulated, that is multiplied with the message signal, and the multiplication is to the phase shifted carrier wave that is multiplied by the message signal with the phase deviation constant for the end for narrowband phase modulated wave. And similarly, we can have the local carrier that is unmodulated, that is added, so of course subtracted or added, that is subtracted with the phase shifted carrier that is multiplied with the message signal that is first of all integrated over time, then multiplied with the frequency deviation constant kf. So that can be seen clearly from figure 4.3. So what we have seen here is that we have the original message which we want to modulate, and we are going to be multiplying with the carrier that is phase shifted. We shifted with minus 90 degrees. Therefore, we are able to have sine of omega t. And this is our locally generated carrier that is not phase shifted. So first and foremost, for the phase modulation, as you can see, it will multiply with the phase deviation constant Kp after you multiply your message signal with the phase shifted carrier. And therefore, when you do the multiplication and then you subtract and you add with the unmodulated carrier, we end up with equation 417 as we have seen right here. And therefore, that is for the generation of narrowband phase modulated signal. And similarly, for the narrowband frequency modulated signal, we are starting first and foremost with an integrator that is going to integrate our signal as we have seen in equation 418, that is going to integrate it over time. And therefore, once we have done that integration, then you're going to be multiplying with the phase shifted carrier that is phase shifted with minus pi over 2 radians. And therefore, when you now multiply with your frequency deviation constant and then you sum them, one is subtracted, the other one is added with the local carrier that is unmodulated. This gives you a straightforward narrowband frequency modulated signal. So these two approaches allows us straightforwardly to generate narrowband phase modulated signal and narrowband frequency modulated signal. And now we want to see how we can generate wideband angle modulated signals. And we see there are two methods. One of them is direct, the other one is indirect. So to start with, we look at the indirect method, and we say that in this method, a narrowband angle modulated signal is produced first, as we have seen in figure 4.3, and then it is converted to a wideband angle modulated signal by using frequency multiplier, as is shown in figure 4.4 right here. And therefore, what we start with is a narrowband signal. You start with a narrowband signal that has been generated using the method that we have seen in figure 4.3. And then when you multiply this with a frequency multiplier, this will produce a a wideband signal. Now the frequency multiplier, consider that the input frequency of the frequency multiplier is this. So this is what you get after you have generated the narrowband signal. Therefore, the output from the frequency multiplier is that every component of the frequency will be multiplied with n, and therefore you see an n introduced at the carrier frequency and an n introduced at the face of the narrowband signal. So there is one disadvantage of doing the direct frequency multiplication, in which case the frequency of the carrier is increased to an abnormally high frequency. And we say to avoid this, we use a mixer or a DSB modulator that is necessary, as you can see in figure 4.5, this figure here. So here we are using a mixer, in which case at this stage here we have just followed the method of frequency multiplication that we have already defined earlier. But after we have generated the wideband frequency modulated signal, we perform frequency translation at this stage, whereby we multiply with the local carrier frequency that was not multiplied with n, and therefore when you do that, you will end up with the, and of course you take it through bandpass filter that is within the range of FC2, and there, or rather we are going to multiply with okay, I think I just need to write this down so that we can see how it comes about. So here I've just brought in the equation that would allow us to show how the frequency mixing or translation would reduce the abnormally high frequency of the carrier after that is attained after you multiply with the multiplier n. So what we do here is that when you multiply with the local frequency oscillator that has a frequency of omega LO, LO I've just used to mean local oscillator, then it is going to cause this kind of multiplication to happen, such that when you multiply y of t with the carrier that is multiplied, that is a function of the local oscillator having the frequency or the angular frequency omega LO, then what will happen is we are just going to apply the sinusoidal the cosine law that says that when you do that kind of thing, you have an addition and a subtraction, such that we are subtracting the LO from the omega C, and therefore we are going to end up with a lower frequency component that is equals to omega LO minus omega C, or vice versa. You can have the difference depending on which one is higher. Therefore, this one is acceptable in comparison to the omega C that was multiplied with omega N that we had earlier. I think here it should have included n and n here. So when you multiply omega LO, or when you subtract omega LO minus minus n omega C, then it is going to, what am I doing here? Then it is going to reduce the high frequency component from abnormally high to a relatively lower frequency component. And to sum this up, we conclude the generation of wideband method. We conclude with the direct method of generating wideband FM signal, in which case we are saying that the modulating signal directly, that is the word that we must get, that directly controls the carrier frequency. And here is the idea that you have the input to the voltage controlled oscillator. The message signal is empty, and the output is a wideband frequency modulated wave. So what happens is that the modulating signal MT is applied as an input to this VCO, and VCO produces an output here that is a function of the MT. So the frequency is a function of MT, and you're saying that the frequency that is coming out is directly proportional to MT. And therefore, we can say that Fi will be equals to the frequency of the carrier plus the deviation constant Kf, then times the MT. So this is the deviation constant that is resulting from this direct relationship. So that is a direct method of generating wideband frequency modulated signal. And we say that the main advantage of this method is that large frequency deviations are possible, and thus less frequency multiplication is required. We have seen that frequency multiplication generates abnormally high frequency component, and which we need to bring down, like we have done here. But for this direct method, we do not have that disadvantage of generating a very high frequency component. Now, the major disadvantage is that the carrier frequency tends to drift, so the additional circuitry is required for frequency stabilization.